Hi, I'm Keenan Casey for TutsPlus.com. In this lesson of Computer Networks Distilled, we're going to be talking about routing protocols. We're going to be at the network layer of this Internet protocol stack. The first question we've got to ask is, what is routing? I'm going to say that routing very simply is finding a path. We're going to send packets from a sender to a receiver over possibly many links. There are many possible paths that could be taken by this packet. What path is chosen? Hopefully it's a good one. Routing is the process of selecting that good path. Let me give you an example. If this sender wants to send a packet through this network to the receiver, it might be routed as follows: through this router, to this router, to this router, to this router, and then lastly to the receiver. So this sequence of 6 links through these 7 hosts, including the routers, is a route. And the way that this path was created seems magical at the moment, but we're going to learn some algorithms that will help us to solve this problem. The next thing we need to think about is the difference between routing and forwarding. Routing, as we've said, is the process of determining the route taken by packets from source to destination over multiple hops. Routing is a very global mechanism. In contrast, forwarding is a very local mechanism. It's the process of moving packets from a router's input to the appropriate output link. So routers do both of these processes. Routers route and routers forward. In this lesson, we're going to be most interested in how routers do routing. To help with routing, we are going to have to deal with some mathematical concepts, namely that of graphs. Remember that a graph is a set of nodes and edges. In this case, our nodes are going to represent routers, and the edges are going to represent links. So you can see, as I've written in this notation here, our routers are named A through E, and they're linked together according to this diagram, and we can name each of those links based on the 2 routers that it connects. So this diagram, this graph of routers, we're going to represent as a mathematical graph with the nodes and edges. The question that we have is, what's the best path from A to E? What do I mean by best? Well, more precisely, we are interested in the least cost path. We're imagining that we've assigned every link some value. This might represent distance or some other cost metric. It might be related to bandwidth or congestion, or it might just be distance. So we imagine in this case that we are trying to find the path between 2 nodes, specifically A and E in this graph, whose complete path cost is the least. And if you look at this graph as a human being with intelligence, you can do some trial and error and figure out what the best path is. What we need to do is find an algorithm that will do that same thing. Find an algorithm that, given a graph, can find the least cost path between any 2 nodes. There are 2 main types of algorithms that have been developed to solve this problem. Those 2 are called link state and distance vector. And I wanted to, on the outset, do a quick comparison between these 2 types of routing protocols. In a link state algorithm, the complete topology of the network has to be known. That means you have to be able to see all of the nodes and all of the links. With distance vector, you only have to know the local topology. Each node just has to know its own neighbors and the link costs to those. A link state algorithm is going to have to broadcast the information, and it's going to broadcast the information about the state of its links to everyone in the network. A distance vector algorithm, on the other hand, is just going to exchange information among neighbors, but it's going to exchange the information about its complete routing table. Link state is a very global algorithm, whereas distance vector is a very decentralized algorithm. This is a nice way to summarize it. Very informally, a node in a link state algorithm tells the world about its neighbors. That is, it tells everyone about its one-hop neighbors. Whereas in distance vector routing protocols, nodes tell their neighbors about the world, about everybody else. If you keep these simple summaries in mind as we get into the specifics, I think it'll help you see the forest for the trees. Let's start with link state. We're going to consider this sample graph, and we're going to be finding a path between nodes A and E. The first thing we'll do is I'm going to simplify this graph, and we're going to store all the link costs up here in the upper left so we can see what they are. The notation for this is we will remember for each visited node the least cost path to it and what node we visited previously to get to that node. So for example, we're going to first choose B. Our goal is to find all the paths from A to every other node in the network. The least cost paths from A to every other node in the network. So first we're going to choose node B. We can see that we can get to node B in 2 through A. Also, node C we can get to in 4 through A. We're going to choose the node with the least cost, which will be B. We can also get to node D through A with a cost of 10. We cannot get to node E directly, so the cost of that is set to infinity, and there's no previous node to get to that. Next, we're going to choose node B as our working node. So we're going to imagine now we're at B. We're going to run this link state algorithm. In this case, we're going to compute the least cost path to all of the non-visited neighbors of B and compute the least cost path. We can get to C through B in 3, and that's because already at 2, and we can get to it through 1. For D, we see we can get to D in 8 because 2 plus 6 is 8. And lastly, we know we can get to E in 11 because our 2 plus 9 is 11. So we store here that we can get to E through B in 11. All right, now we add B to our checked set, and we're going to select another node with the smallest value, which looks like it should be C. So we choose C. Now we're going to check all of the neighbors of C and see if we can find any better least cost paths. We can get to C through B with the cost of 3, and for 4 more we can get to D. So that means we can get to D through C with a cost of 7. That's lower than our previous cost, so we'll update that. Next we add C to our checked set, and we move on and make D our working node. In this case, we check the neighbors of D that are not in our checked set, which is only E. How much does it cost to get to E through D? Well, we're already at 7, and it's going to cost 2 more, so that means we can get to E in 9. 9 through D is smaller than 11 through B, so that's the route that we'd like to save. Finally, we update, we choose E. E doesn't have any connected nodes, so now we're done with E. We've checked the whole graph, and we found the least cost path. You can kind of imagine here by working backwards through these predecessor nodes that we've stored, we have found this path from A to B to C to D to E is the least cost path from A to E. We can almost even imagine that those other links, the ones that are more expensive, are not there, and we will route through the least cost tree that's associated with this subgraph that we've discovered. This is the link state algorithm. Specifically, I've shown you Dijkstra's algorithm to compute the shortest paths given a complete network topology. The second type of algorithm that I want to show you is the distance vector algorithm. Remember that in this algorithm, nodes tell neighbors about the world. First, we need to define what a distance vector is. A distance vector is simply a set of values that represents the distance from you to everyone else in the network. For example, at A has the following distance vector. It knows it can get to itself in 0, it can get to B in 2, it can get to C in 4, and it can get to D in 10. It has no link to E, so that value is set to infinity. Likewise, at B has the following distance vector, which is all of its one-hop neighbors, 2 to A, 0 to itself, 1 to C, 6 to D, and 9 to E, because it's directly connected with E. B has the following distance vector. Note that it's not connected to E, so that value is infinity. D has this distance vector, 10 to A, 6 to B, 4 to C, 2 to E, and 0 to itself. E has this distance vector, infinity to A because it's not connected, 9 to B because it is connected, infinity to C because they're not connected, 2 to D, and 0 to itself. So those are the 5 distance vectors for each node. Now, the distance vector algorithm works by iteratively exchanging these values and computing a new routing table based on the distance vectors that are received from your neighbors. So A, since it's connected to B and C, will receive these 2 distance vectors. It'll get this distance vector, which is what we just found at B, and we know that the delay from B, cost to B, is 2. We'll receive this distance vector from C at a delay of 4. Now what can we infer from this? Well, we know that we can get to the same nodes that are listed here through node B or node C if we pay this delay. So for example, A knows that it can get to itself in 0. The first interesting one is how can we get to B? We can get to B by going through B, which is a cost of 0 plus the 2 delay. Or we can get to B through C, which would be a cost of 1 to get to B through C plus 4 to get to C. In that case, the shorter path is 2 or 5. Certainly the 2, so we're going to store that we can get to B through node B in 2. As we keep going, let's evaluate the cost from A to C. Well, A knows that it can get to C in 1 through B plus the delay to B, which is 2. Or it can get to C directly at a cost of 4. And C can get to C with 0. In this case, we actually have found some new information here. What's the minimum of 1 plus 2, or 0 plus 4? 3 is smaller than 4, so it's faster to get to C through B than simply by going straight to C. So in this case, we store that we can get to C through B with a delay of 3. Let's do the same thing for D. We can get to D from A through B with a delay of 6 plus 2. We can get to D through C with a delay of 4 plus 4. So this ends up being the same as of this moment. Note then we could choose either one since they're tied. Choose the 8 through C and store that. Note that this isn't optimal, but we'll have to iterate this algorithm several more times to find the optimal route. Lastly, A is looking for a route to E because it doesn't have one, and note now we're able to find one. In this case, we know we can get to E through B at a cost of 9 plus 2, or we can get to it through C. No, we can't because it still has this infinity. Infinity plus 4 is certainly too large. We learned that we can get to E through B in 11. Now this isn't the optimal route, but we will learn it over time. So what do we do from here? We rinse and repeat. The distance vector algorithm continues iteratively and will eventually converge on the solution to the shortest path as long as these distance vectors keep being exchanged by neighbors in the network. Over time, this information will spread and the best paths will be found. So this is how distance vector works. Let's compare these two routing protocols. Link state algorithms are going to send out more messages because they have to broadcast them, whereas distance vector only has to exchange with neighbors. The message size for link state may be smaller because it just contains link costs, whereas in distance vector we have to send the entire distance vector, so the message size will be larger. The convergence speed means how fast do we converge upon the correct solution to the shortest path problem. And for link state algorithms, it's very fast, whereas distance vectors really do take some time to converge. Perhaps the biggest deal here is the robustness. Link state algorithms are much more robust to changes in the costs. Costs change, if links go down, distance vector can have some very big issues dealing with that. The final topic in terms of routing protocols is a look at how routing really happens in the real world. The real world, as you know, is big and complex, and we've made some simplifications in explaining this. In a very complex network, how is routing performed? It turns out that the best way to handle this is to divide the routers into different areas, different autonomous systems, and then hierarchically route among those systems and within those systems. So we're taking a divide and conquer approach. We can imagine here that each of those different clouds is a different autonomous system, and we're going to break our system into chunks, but link it at certain points. As we see here, we have 3 autonomous systems defined, AS1, 2, and 3. Within each system, they can be running a different routing protocol, but between the systems, they all have to be running the same exterior routing protocol. Within an autonomous system, an Intra-AS routing protocol is run. The goal here is just to route within that autonomous system. The main things to keep in mind with these types of routing protocols is that there is centralized control since one institution is running this routing protocol, and therefore performance is the primary objective. Some examples of protocols that are Intra-AS routing protocols include RIP, OSPF, and EIGRP. And you can see that we have represented here one protocol from each of the main classes. The routing information protocol is a really old protocol that works using distance vector. OSPF uses link state, and this EIGRP is a proprietary protocol from Cisco. So these are three real protocols that an institution that runs a set of routers might use within their institution. How does routing happen among those autonomous systems? One protocol, BGP, the Border Gateway Protocol, is the standard protocol to route among these systems. What does BGP do? It does several things. It obtains subnet reachability information from different autonomous systems. It propagates that reachability information to the internal routers, and it determines good routes to subnets based on the reachability information as well as policy. You see, that's one big point that's new on Inter-AS routing protocols. In this case, policy may be more important than performance. It may be more important that this route not go through some foreign country than it be fast. Or it may be important to keep data from going over a competitor's network. So policy is important. Scale is also important. If we're going to be doing this Inter-AS routing at a fairly global scale among all of the autonomous systems in the world, we need to make sure we can do that in a performant way that scales. So this is just scratching the surface. There's a whole lot of complexity connected with BGP, but it is the Inter-AS routing protocol that routes among autonomous systems. Let me give you a visual explanation of the difference between Intra-AS routing and Inter-AS routing. As you can see here, each of the autonomous systems in this network is running a different Intra-AS routing protocol. Externally, between the autonomous systems at these border routers, each of the border routers must be running the same BGP protocol so that they can talk to each other and route among the autonomous systems. As you can see here, these links are the ones that would be exchanging the BGP information externally among the different autonomous systems. The main question we've dealt with in this lecture is, how do routers find global paths? The answers we've seen are link state, distance vector, these two main classes of routing protocols. And in the real world, we use a hierarchical organization with Intra-AS and Inter-AS routing protocols to make everything work together when scale matters, when policy matters, and when performance matters. So this has been a look at routing protocols in the network layer. I'm Keenan Casey for TouchPlus.com. Thank you for watching.